Hello everybody, and welcome to the start of section 14.4. We're looking at page 38 in the workbook, and this section introduces two of the most important concepts of our entire course, the idea of gradients and directional derivatives. Just to give you a little taste of what's to come here, we've talked a lot about rates of change up to this point, okay, but it's been very specific. We've talked about how to find the rates of change of a function of two variables in two specific directions, in the x direction or in the y direction, assuming that x and y are our input variables. And in this section, we're going to generalize that so that we could find the rate of change of a function in any direction. That's what a directional derivative is. Okay, and it's going to take us a little while to get there. So we're going to start with definition. Okay, and the idea of the gradient. So let's read this together. The gradient vector of a differentiable function f at a point a, b, first of all, we have a special notation for it. It's written either grad f of a, b, or like this with the upside down triangle. We'll usually use this notation because it's shorter. So I'm just going to read that gradient of f at the point a, b. And here's how that gradient is defined. Okay, the gradient is just a vector, and its two components are partial derivatives, the derivative with respect to x and the derivative with respect to y. Okay, so in the preliminary example below here, we're going to just do some calculating. Okay, calculate the gradient and try to make some geometric observations about what it's telling us. Okay, so let's read the statement of the preliminary example here together. So the temperature at a point xy on a metal plate is given by T of xy equals 1 minus a fourth x squared minus a fourth y squared. Okay, and we'll assume that x and y are both measured in centimeters. And information about this function is being given to us in two forms, level curves and as a graph. Okay, so notice from both of these pieces of information, we can kind of see a little bit of qualitative information about how the temperature is behaving. Okay, so the temperature, notice that it's getting warmer as we move closer to the origin. And you can see that over here in the graph as well, because our temperature function reaches a peak near the origin. Okay, so that's kind of the setup. Let's move down to the first part of this question, part A, see what they're asking us to do. Okay, so they'd like us to calculate the gradient of t and to use our formula to fill in this table that we've got down here, and then finally to sketch the vectors, these gradient vectors, on the contour diagram above. All right, and what I'd like to do is to maybe do a couple of entries in the table, ask you to pause the video and see if you can fill in the rest of it. Okay, so first let me get rid of just some of these markings that I made here. Okay, and if we want to fill in gradient vectors, then we need to calculate the gradient first. So let's take a peek how the gradient was defined again. Okay, the gradient is just a vector that consists of partial derivatives. So our first step is going to be to calculate partial derivatives. All right, let's see if we can sneak that calculation in here. So the formula for our function, that's sitting right here. If we want to take the derivative of that with respect to x, notice that only the second term is relevant, because that's the only term that has x's in it. The other two terms are going to go to 0. So the derivative of negative a fourth x squared is just going to be negative a half x. Okay, the derivative of x squared is 2x. And similarly, the derivative with respect to y, the first two terms are going to go away, and we're just going to end up taking the derivative of the third term. That's going to give us minus a half y. Okay, so those are our two partial derivatives, which means that the gradient, by definition, is just the derivative with respect to x, I, plus the derivative with respect to y, j. Okay, the two components are just those partial derivatives that we calculated. Okay, and now that we've got the formula for the gradient, we want to go to the table and just start filling in entries. So we'll start with the point 1, 0. Okay, and remember, the 1 and the 0, those are just x's and y values, so the idea is just to substitute those x's and y's into our gradient formula here and see what we get. I'm going to see if I can sneak that calculation in here. So gradient t, -1 and 0. We just take x equals -1 and y equals 0 and substitute it into the formula that we got over here. And if you do that, make x -1, you're going to get a half I. And since y is 0, the j component is going to go away. Okay, so our final result, the gradient at -1, 0, is the vector 1/2 I. Okay, what about -2, 0? Okay, well, same thing, just that this time we're plugging in -2 for x and 0 for y. So again, going back to our formula over here on the left, if we plug -2 in there, we're going to get just I plus 0j, okay, which gives us a result of I. Okay, get rid of a little of the clutter here. And now, let's see if we can plot those gradient vectors. All right, starting with the gradient at -1, 0. So first what we're going to do is to find the point -1, 0. That's sitting here, x is -1 and y is 0, and then we want to plot the vector 1/2 I. That's going to take us a half of a unit to the right. There's the gradient vector. Okay, let's do the same thing at -2, 0. Okay, so if we find that point, that's sitting over here. And the vector that we want to plot this time is I, so that's going to be a full unit to the right. Okay, and there's our gradient vector. Okay, now at this point, I'd like you to actually pause the video and see if you can fill in the rest of this table on your own and then plot the gradient vectors. It'd be a nice exercise. Okay, welcome back. So hopefully you've given a shot to actually filling in the rest of this table. I'm going to go ahead and just fill in the rest of the values and the gradient vectors so that you can check your answers here. Okay, so if x and y are both 1, then we're plugging 1 for both x and y in here. That's going to give us -1/2 I minus 1/2 j. Okay, so if we go to the point 1, 1, that's going to put us here at P. And we want to go -1/2 to the left and -1/2 to the right. That vector is going to look like this. Okay, and then similarly, let's go ahead and fill in the last two. Okay, square root of 2 over 2, that's not such a nice number, but it's maybe about 0.7-ish. Okay, so let's see, 0 square root of 2. That's going to be this point right up here. And we want to go straight down, -√2 over 2. So just roughly speaking, that's going to take us about to there. Okay, and 0 -√2, that's sitting down here. It's going to take us up to about there. Okay, so we have taken the gradient in a few places. We have plotted the gradient vectors, and now I'd like to see if we can make some observations. Is there anything special about those gradient vectors that we plotted? Okay, well, one thing that you might have noticed as you're doing this is that all of the gradient vectors up here seem to be perpendicular to the contours. That's one observation that we could make. Okay, another thing you might notice at the same time is where those vectors are pointing. They're all pointing to the origin. And what's special about the origin? That's the place where we're getting the absolute greatest temperature, if you look over here at the graph. So we could say that the gradients are pointing in the direction of maximum temperature increase. Okay, so two kind of interesting observations there about those. Okay, and then another thing, what about the lengths of the gradient vectors? Okay, some of them are longer than others. For example, the one over here, that was a really long vector. And the one over here was much shorter, even though it points in the same direction. Do you notice any patterns as to where the vectors are longer, where the gradient vectors are longer? Well, if you stare at the picture a while, you might notice that where the level curves are closer together, like over here, we're getting longer gradient vectors, and where they're farther apart, nearer to the origin, those gradient vectors are shorter. Okay, so let's try to put that into words. Okay, we'll say it this way: longer where the level curves are closer together. Okay, so the length of the gradient vectors appear to tell us something about how fast the temperature is changing. Okay, and we'll see that both of these observations are true in general as we continue with this section.